All right, today we've got 8.3 exponential functions. So our objectives are to graph exponential functions and then apply exponential functions to compound interest. All right, so here's a question for you. Would you rather have $300 added to your savings account each year or have it earn 3% annual interest? Quite honestly, the answer depends on the amount that you've invested, or P, and the duration of the investment, which we're going to represent as time. Okay, so we're going to look into more of that. That's that compound interest idea. So an exponential function, okay, is a function of the form y equals b to the power of x, where b is greater than 0 and b is not equal to 1. One thing you need to know here too is that this y equals b to the power of x, this is our parent function form. Okay, so parent function form. All right, so it's going to be an increasing function when b is greater than 1. So the value of y increases as x increases. And it's going to be a decreasing function when 0 is less than b, which is less than 1. So this is when the value of y decreases as x increases. So the closer the base b is to 1, the more gradually the function increases and decreases. Okay, so again, the closer the base or the b is to 1, the more gradually the function increases or decreases. So if we look at this graph of y equals b to the power of x, okay, so the domain equals all real numbers. Our asymptote we have is y is equal to 0. If b is greater than 1, it's increasing. This might make some more sense later. Our range is equal to y such that y is greater than 0. Our y-intercept is 0, 1. And when we have 0 is less than b, but b is less than 1, it's decreasing. Okay. So an asymptote, let's go back here, is a line that a graph approaches but never intersects. Okay. So in our first example, 1, okay, or so example 1 there, the x-axis is the asymptote. So the line is going to get close, the graph is going to get close to it, but it's never actually going to cross it in an exponential function. Okay, so let's actually look at some of these because it's entirely new. So graph 1, it says, or example 1, it says graph the exponential functions. Y equals 2 to the power of x, y equals 3 to the power of x, y equals 1/2 to the power of x, and y equals 1/3 to the power of x. So notice y equals 2 to the power of x. So like we talked about that, let's look at that parent function, right? We have y equals b to the power of x, okay? And if we look at that information about our graph, so our graph is going to be it's an increasing function when b is greater than 1. Okay, and then when it's a decreasing function, sorry, I should say, so it's a decreasing function when 0 is less than b, but b is also less than 1. So we can look at these and say, well, which one is going to be increasing? Which one is going to be decreasing? Okay, well, if we look at this, b, we have a 2 here, so this should be an increasing function. 3 should be an increasing function. 1/2 should be a decreasing function, and 1/3 should be another decreasing function. All right, so they gave us a chart, okay, of these numbers, and then we have the graph. I went ahead and gave them all to you. So the question then is, how do we graph these? Can you figure out how do we graph them? Yeah, I'm putting in so I picked my x values, -3, -2, -1, 0, 1, 2, 3. I'm plugging them in for x. So this one here, I have 2 to the negative 3 power? Well, that's equal to 1 over 2 cubed. And 2 cubed is 8. So that's where the 1/8 came from. And then for the next one, we have 3 to the negative 3 power. Well, that's equal to 1 over 3 cubed, because the negative exponent means it should be moved into the denominator. And 3 cubed is 27, so that's where 1 over 27 came from. Okay, so these values, okay, when we have x is negative 3, but in 2x, so if I look at this, these numbers, this is my 2x column. What are these numbers doing? 1/8, 1/4, 1/2, 1, 2, 4, 8. They're getting bigger. It's proving that this is an increasing function. If we look at the 3 to the power of x, and look at those numbers, 1/27, 1/9, 1/3, 1, 3, 9, 27. These numbers are increasing. If I look at the 1/2 x, what's happening to my numbers here? 8, 4, 2, 1, 1/2, 1/4, 1/8. These numbers are decreasing, just like we said it should happen. And here, 1/3 to the power of x. If we look at those, we had 27, 9, 3, 1, 1/3, 1/9, 1/27. Those numbers are also decreasing. So those are decreasing functions. Okay, so we can start so both of those are proving that. So if we look at these the way they look, we can also see that. So here's the 1/2. So we've graphed it, and it's a decreasing function. So it's getting close. It's going to keep rising further and further and further away from the x-axis this way. But here, it's going to get closer and closer and closer to that x-axis. It never actually touches it. Okay? You're never going to get a 0, 0 on an exponential function. Whereas if we look at one of these others, like y to the power of 3x, okay, it's increasing. It's really, I just crossed it, so that's not exactly the best thing. But those numbers, if we graph them for the 3 to the power of x, those numbers are increasing. So they're getting close to 0. I still look like I crossed it, and I went on the wrong one. So we'll look at the 2x, or 2 to the power of x. So down here, they're getting close to that 0, or that x-axis, but technically never crossing it. Your drawing may cross it, but it's okay. It doesn't actually cross it. All right, the graphs of exponential functions of the form y equals ab x, or to the power of x minus h plus k. What? Okay, these are the transformations of the parent. These are transformations of the parent. That's what it says right here. So to do our translations, we have our h's. Okay, I'm going to draw a line through here. So our h is here. Okay, if it's greater than 0, notice our h. It's going to be right. If it's less than 0, we're going to translate it left. Our k values, if it's greater than 0, it's going to go up. If it's less than 0, it's going to go down. So here's k. Our a value, the absolute value of a, if it's greater than 1, it's going to be steeper. If it's less than 1, but more than 0, because we're not going to have negatives, then, or if we don't have a negative, it's going to be flatter. And so this would be like a fraction. Let me write that in there. Maybe that would be helpful. So if this was a fraction, okay, then it's going to be flatter. Now here, if a is less than 0, so if this is a negative number, that's what this is talking about, then it's going to be a reflection across the x-axis. A reflection across the x-axis. So we're going to transform these parent functions. Okay, let's give this a whirl. Okay, example 2. We're going to graph g of x equals negative 3 over 2 times 2 to the power of x as a transformation of the parent function f of x equals 2 to the power of x. Then describe g of x by stating its domain, range, y-intercept, and the equation of any asymptotes. Woo! Okay, so essentially we're going to graph both the g of x and the f of x. So I'm going to set up a chart just like we had earlier. So I'm going to pick out some x values. Let's do our parent function first. So that 2 to the power of x, and then we'll do our other one, the 3, a negative 3 over 2 times 2 to the power of x. I guess we'll call that our child function. All right, and I don't require you to go all the way to negative 3, but I do always want to see like 5 numbers. So we have 0 and then the 1 on both sides, negative 1 and 1, and then negative 2 and 2. So 2 numbers on both sides. Okay, so remember we're plugging, so that's our setup. Let me change colors here. We're plugging our x value in for x. So this is 2 to the negative 2 power, which is equal to 1 over 2 squared, which is 1/4. So I would graph negative 2, 1, 2, and then 1/4. Kind of hard to see there. Okay, and then I'm going to have 2 to the negative 1 power, which is equal to 1 over 2. So I'm going to graph negative 1, 1/2. So negative 1, 1/2. Kind of looks like it's in the same place on this tiny graph. I should have made my graph bigger. But the problem is the numbers get big fast. So 2 to the power of 0 equals 1. Anything to the power of 0 is 1. So I'm going to graph 0 and 1. And then I'm going to do 2 to the power of 1. Well, that's 2. So I'm going to graph 1, 2. So 1, 2. See, my numbers are starting to jump a little bigger. Now I'm going to have 2 squared. Well, that's 4. So I'm going to graph 2, 4. So 2, 1, 2, 3, 4. All right, so this is my, I'm going to bring that on out because it's close to that x-axis here, but it shouldn't cross it. Again, even though my picture does. All right, so this is my parent function, my f of x equals 2 to the power of x. Okay, let me change colors. Let's do our other one. So we're going to have negative 3 over 2 times 2 to the power of negative 2. Which is kind of nice. We already did that, right? We already did this math. So this is going to be negative 3 over 2 times 1/4, right? That makes it a little handier that we already have that answer here. So this is going to be negative 3/8. So I would graph negative 2, negative 3/8. So negative 2, negative 3/8, which is almost a half. Didn't get down there. Okay, so then the next one, we're going to have negative 3/2 times 2 to the negative 1, which is equal to negative 3/2 times 1/2, which is equal to negative 3/4. Okay, so I'm going to do negative 1 and negative 3/4. So this one should have been up here. Let's see, maybe I can try to do better on my dots. Perhaps. Oh no, I'm erasing all my work. Never mind. Negative 3/4. I just realized. Let's see if I can get my eraser up in there. That's better. Okay, so let me go back and do my negative 2 and negative 3/8. So negative 2, negative 3/8, negative 1, negative 3/4. Okay, so then we're going to have negative 3/2 times 2 to the power of 0, which is just negative 3/2 times 1, which is negative 3/2. So that's negative 1.5 when you're graphing. That might be more helpful. So 0, negative 1.5. And then negative 3/2 times, I'm going to take the shortcut because this is going to be 2 to the power of 1, but I already know 2 to the power of 1 is 2. So, which is just going to give me negative 3. So I'm going to graph negative 1, or I'm going to graph 1, negative 3. So 1, negative 1, 2, 3. And then for the last one, it's going to be negative 3/2 times 2 squared, which I know is 4. So that's going to give me negative 6. So I'm going to graph 2, 1, 2, negative 6. 1, 2, 3, 4, 5, 6. So there is my graph of g of x, which is that negative 3/2 times 2 to the power of x. Okay, so then describe g of x by stating its domain, range, y-intercept, and the equation of any asymptotes. Okay, so you'll notice, right, that we had a negative number here. Okay, this negative number meant it was a reflection, which we see that it did, it reflected. Okay, we also had a 2x. Okay, so our 2 was our a value, so it was steeper than our fraction. When we had our fraction, okay, because it's the absolute value of a, so 3/2, it was a little bit flatter. A little bit flatter graph. Okay, so let's go back to the things. Let's state the domain, the range, and all that stuff. So our domain is up first. Okay, remember our domain is our x values. So our x values are going all across here. We have our arrow going this way, our arrow going down, which means it's continuing on, and as it goes down, it's also going to the right. So our domain is all real numbers. Our range, on the other hand, is not. It has a stopping point. So it would help if we knew our asymptote, right? This x-axis is our asymptote. So ASY, that's a funny spelling, right? MP, asymptote. Asymptote. Okay, so that's where our stopping point is. So our range is going to be our y, such that y is less than 0, because it's never going to be equal to 0 either. Then we were supposed to do, let's see, domain, range, y-intercept. Y-intercept. So where does our asymptote cross 0? Well, we calculated it, right? When x equals 0, yeah, so our y-intercept is, sorry, I had a brain fog there for a second. So 0 in negative 3/2 is our y-intercept. Okay, and then our asymptote. We want the equation of any asymptote. So you can't have more than one. In this case, we just have one. But our asymptote, okay, what's the equation of that line? It's the x-axis. So our equation is y equals 0. Whew, there's a lot there. A lot of information. Okay. So let's clear that and go to the back. Okay, example 3 then. We're going to graph f of x equals 5 times 2 to the power of x minus 1 minus 3 as a translation again of that parent function of the parent function f of x equals 5 times 2 to the power of x. Then describe f of x by stating its domain, range, y-intercept, and the equation of any asymptotes. Okay, so let's set up our table, and we'll do our parent function first. So we're going to do -2, -1. Let me space those out a little bit more. -1, 0, 1, and 2. Okay. So we're going to do our parent function first. 5 times 2 to the power of x. Okay, so this is 5 times 2 to the -2 power. Okay, remember the exponent only applies to the number right in front of it. And so that's the same thing as saying, okay, well, this is 5 times 2 to the second, or 5 over 2 squared. Let me back this up maybe to show you. It might be helpful. Okay, so this is 5 times, when we have that negative exponent, it means it needs to go in the denominator. So this is 5 over 2 squared, which is equal to 5 times 1/4, which is equal to 5/4. So I would graph -2 and 5/4. So 1, 2, and 5/4 is just above there. Okay. Then this is going to be 5 times 2 to the -1 power. So I'm going to skip this step here a little bit. So this is going to be 5 to the 1/2 power, which is 5/2. So I'm going to graph -1 and 5/2, which is 2/2, 4/2, 5/2 would be there in the middle kind of. Okay, then we have 5 times 2 to the 0 power, which is 5 times 1. So 5. So I'm going to graph 0 and 5. 1, 2, 3, 4, 5. So this one's increasing very quickly. This is going to be 5 times 2 to the first power. So 5 times 2 equals 10. So it's 1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Way up there. Okay, so it never crossed that x-axis. Okay, so there's our line there. We can go ahead and do the 2, but we know, or the power x to the power of 2, we know it's going to be off the charts, but that's okay. So then it's going to be 5 times 4, which is 20. Okay, so I'm going to erase some of this work here. Hopefully you've got that all down. And then we're going to do our next one. So we have 5 times 2 to the x minus 1 minus 3 power. Now, if you remember, like if you look back to the front of this, and you know what all those translations do to our parent function. Like once you have the parent, like you've got this done here, you can be like, oh wait, this -1, doggone, my color didn't change. This -1 means I'm going to, if I look at that up there, that's my h value. And if my h, so here, right, because if I, let me actually write this down. So my regular form is y equals ab to the x minus h plus k power. Okay, so I have x minus, so my h here is equal to 1, which means if h is greater than 1 or greater than 0, I'm going right. So here I'm going to go right 1. Okay, then my k is the number here, and I have, on my problem, I have -3. It's kind of hard to see, but I have -3 in there, so my k equals -3, which means that I'm going to go down 3. So I'm just going to translate what I have, right 1 and down 3. So instead of doing all the math, you could take the shortcut and just take this point and say, okay, I'm going to go right 1 and down 3. 1, 2, 3. And so it's like right here. Right 1, down 3. 1, 2, 3. Right 1, down 3. 1, 2, 3. And then you can graph your f of x there. Which really should have been a g of x. They shouldn't both be f of x. So, intriguing. Oh well, it's okay. Next, we need to do the domain, the range, the y-intercept, and the equation of any asymptotes for this one. Okay, so first of all, we're gonna, I think maybe I have to erase some stuff, but I can probably make it work. Let's see if my color changed. It did. So we'll just put it in red. All right, so our domain is up first. Our domain is up first. What is our domain here? What is our domain? Good, it's all real numbers, right? Because domain is our x values. So our domain is all real numbers. How about our range? What's our range? Okay, remember, we're looking at the green one. Okay, so what is it getting close to, right? This should be y. That's a terrible mark. Such that y is what? Okay, so we should be able to look like this one is 1 above our 0. This would be our asymptote here. So then it would be 1 away here, and that's negative 1, 2, 3. So this should be y such that y is greater than negative 3. Okay, let's do our y-intercept. Okay, so where does this asymptote cross the y-axis? Okay, so where is x 0? Well, when x is 0, it's at 5. Hold on. Not 5, that's our blue one. Yikes! So this is the one time when it's helpful to do the math. But this would be, if we did that, so we would have 5 times 2 to the x. Okay, so the 0 minus 1 minus 3 power. Okay, so 5 times 2 to the negative 1. Right, that's 2 to the negative 1 minus 3. So 5 times 1 half minus 3. So this is 5 times 1 half is 5 halves minus 3. Okay, 3 is 6 halves, so this is 5 halves minus 6 halves. So that gives us negative 1 half. So our y-intercept is at 0, negative 1 half. We might have to look at that. Feel free to ask me some questions on that in class, but that would be the one problem in here that you would have to solve, unless your graph was better than mine and you could tell a little bit easier. But it's always better to solve the equation. All right, then the last one is equations of our asymptotes. Okay, so our asymptote here. Again, we can see, like in this one, this point was like a 1 away from our x-axis. So when we move that point down, we moved it right 1 and down 3, it's 1 away from 3. So this is our asymptote. If everything else shifted down 3, our asymptote shifts down 3 as well. So our asymptote is y equals negative 3. Okay, I'm actually going to stop there, and we'll look at compound interest separately. Okay, so I'm going to stop there today for 8.3. All right, see you later.